So before I start, I have a personal disclaimer to make. So I was with Siemens Healthineers for a long, long time. It's like really a veteran engineer there, basically. And I was located in Princeton for about 14 years. But recently, I moved back to China. So working for Chinese Academy of Sciences. It's located in Beijing. It's really a fresh job, so it's like just 2 months. So I'm really a rookie professor here. It turns out this is kind of like my first lecture to such large audience. So please bear with me if I made anything funny or anything. So this is the outline of my talk. So I will first give a brief overview of medical image parsing. And then I will move on to talk a little bit about, how we tackle the challenge, really the pre-deep learning era, where, essentially summarize some of the work I did at Siemens. And then I will move on to talk about deep learning, how can we combine deep learning together with knowledge to do medical image parsing as well. So first of all, just to give you a very quick overview of medical imaging, I think everybody knows the importance of this, and I like the numbers here. For example, healthcare itself is about like 20% GDP, 20% of GDP of USA. And then within healthcare or medical data, 90% of medical data are actually images. So this is really a huge arena for all of us to play around. And then then I find that there are 3 trends in medical imaging. Number 1 trend is that there's like millions of modalities. You can look at image, you look at the patient, or look at the objects in various ways, right? You can look at the anatomy through like clinical scans, like on this side, and then you can pretty much zoom in all the way down to moleculars. And then this is really like a multi-scale phenomenon, and it creates a lot of data. There's also an interesting thing is like, if you are inventor of these imaging cameras, for medical images, you have higher likelihood you can receive Nobel Prize, right? So starting from, X-ray, and then you have CT, you have MRI, and then all the way, all kinds of microscope, essentially down the scale where you can look at sub-nanometer structures, right? And then the latest one is really happened like last year, where this chiral electron microscopy won the Nobel Prize in chemistry. So this actually we have a hope by working on medical images, at least we are getting closer to Nobel Prize than any other engineering discipline. And then the second trend I see strongly, in particular when I work at Siemens, where essentially even within one modality, you see information get more packed, basically, in every pixel, in every voxel, right? So this is an example of ultrasound images back in 1953, where you see, I actually don't know exactly what's been displayed here, to be honest. But on the right-hand side, which is really coming from the latest cardiologist ultrasound scanners. And hopefully you can see that, it's a video playing, and this scanner has amazing capability. It can acquire like about 100 frames per second, and each frame itself is a 3D volume. So this is huge amount of data collected nowadays. And then by looking at this kind of data, you can really imagine, how many things you can see from this, empowered by this kind of data. And the same for the MRI. So on the left, was really like, I believe it's the first picture coming off a Siemens scanner. And then you can see, you don't see too much basically, all right, from this picture. But on the right-hand side is really also MRI images. And here you can see a lot of details, what's going on inside the brain, for example, right? And particular on this part is really like using the modern rendering technologies to display MRI images. So it seems like you can even see more information. And this actually coming from a 7 Tesla scanner where you can see all the fiber connections within the brain. And same story happens for CT. This is again, I think it's the first image coming off Siemens scanner back in '74. And this is a CT image. I don't know if you can believe it or not, but it is a CT image. It is just rendered differently. So with all these different modalities and then all this more information is packing into each data, so which basically creates a challenge for us, right? So this is, I think, really I see a trend coming very strongly. How can we use AI to analyze those data? So to me, this is really the holy grail of medical image analysis problem. So in the way that given an image, what I want is to assign labels to every pixel, to every voxel, if possible. And I should say, like, I should recognize whether this voxel is part of the lung or part of the liver. Is this a bone? If inside the bone, right? Is this a part of a lesion? Is this part of the fraction? And everything you can imagine. So it turns out this is like huge amount of knowledge you should do with. For example, if you only look at the anatomy point of view, and there's this foundational model of anatomy, it describes a huge number of classes, like about 75,000 classes. And then let's look at, this is more like look at the disease, the findings and disease, and same amount of information, knowledge you can find basically. So your task is really like assign a pixel, a voxel to labels in this dictionary. So this is a huge amount of complexity you can imagine, right? It's like if in a typical, say, CT volume, you have millions of voxels. And every voxel, you have to pick a label out of this amount of classes. So you can imagine the complexity of the problem. So that's why it actually really makes us busy for a long, long time. However, this is really very beneficial if you can really do so. So you can benefit on many different things, right? So I think we had a discussion how we can do this on the scanners. If we have a very good analysis method, understanding the anatomy, understand disease, we can make the scanner more personalized. And the scanning will be more consistent, regardless of the users, right? And we can even make the scanning faster. And if it's CT scan, we can actually use radiation to our patient. And then, of course, we can also use this to help to do the screening and diagnosis. So where we can make the reading more structured, we can help quantify more clinical problems, and we can make the workflow more streamlined, and even make a report out of the reading. And go down further the stream, so we can talk about therapy and the surgery. So we can actually plan a surgery based on the findings in the images, or we can even predict if a therapy will be successful and monitor the progress of therapy. So this is really a huge benefit of doing so. Of course, this problem is not without challenge. So the main challenge I feel is essentially it happens in the following, right? So first of all, you can see a lot of appearance difference. So this is just a tip. This is just one example, right? So if you know CT, that if you want to look at the vessels, you need to inject contrast agent. So that actually lights up the image, also lights up the vessels. And on the left here is really a CT scan without any contrast agent. So you can see huge difference between these two type of inputs. And then, of course, we are talking about medical images. Most of the medical images really taken for reason because you suspect some pathology and so on. So which is basically creates some kind of difference, right? So whether maybe the organs is distorted, maybe sometimes even the organ is dissected, so it's missing, and so on. And then another, I think, kind of overlooked problem is really here, things are always have a very narrow field of view. Because you don't want to, say, take a whole body CT for no reason, right? Because that creates a lot of radiation to the patient. So often you want to minimize those, so hence you only take a subpart of the body, and that actually creates a lot of issue for processing, because a lot of your model maybe assumes that the organ has to be there and so on. So it's really like, I wouldn't call it a collusion, but it's really a largely structural missing problem. So just to give you some ideas, right? This is just showing the pictures of bones, all right? So this is really, on the top is a femur and the bottom is a tibia. And then if there's a diseased knee joint, and you will see different kind of appearance. So a normal joint, you will see a nice gap in between these two bones. All right, so which is basically the cartilage cannot be seen in the CT. But if there's this kind of pathological bones, and then you can see these bones touch each other. Hopefully you can see it. It's rather difficult to see, but you can roughly figure out this is touching each other. And as you know, that this will create a lot of trouble for segmentation, for example. And then, of course, there are many pathologies, and this is one example of osteoporosis. So where you can see a lot of stuff going inside, and there's even some kind of bone loss happening around this boundary of the femur. And this is actually almost like a broken situation. And then there will be like metal implants inside the bone already. So all these creates a lot of variations for your segmentation algorithm, for example. So you have to deal with all these. And this is just for bone. And if you know medical images, you probably know that bone analysis is a relatively easy task. Right. And then there's additional challenges. So if you really want to push the solution to clinics, and the solution has to be really robust, right? Ideally, there's no outlier, or at least you can claim that I cannot deal with the image, so that you don't make mistakes. And then if you make some guess of your result better to be very accurate. So one way to measure the accuracy is really compare your result with expert annotations, right? So ideally, your algorithm performs like a user, so the performance is really within the inter-user variability. And another one is really often quite challenging in practice is about the speed. So this is one of the things, actually we used to struggle quite a lot early on, because when we got the training in schools, we often care more about the accuracy, less on the speed. But when you start working for Siemens and you understand that the important speed, because if your algorithm is so slow, no physician will use it. They are really highly paid people, and they don't want to waste their time. So often, just to give you an idea, right? So if you have a CT volume, let's say a thoracic region, usually you end up like, say, 300 slices. So which basically means like 10 seconds video if you play slice by slice. So it's 10-second video, but you only have like a very few seconds to find out what's going on, right? So where's the, say, tumor and so on. So this is highly challenging in terms of computation. However, I just said a lot of difficulties, of course, but there's also quite some opportunities to this problem. So one of this is, obviously, we do have a lot of data available, and every day and every minute, actually, there are more data is being acquired. Of course, try to get access of data is another challenge. And then another opportunity is really we are looking at humans, all right? So there's a lot of knowledge we can leverage. So this actually naturally leads me to study this approach, which is combining machine learning with knowledge modeling. And ever since I joined Siemens 14 years ago, I was really working on this type of approach. Okay, so just to give you a quick summary of what is machine learning and plus knowledge, right? What kind of machine learning you can do? And on machine learning side, I think everybody knows, like, you have supervised learning. You can do, nowadays, of course, everybody will use deep learning. But before, when I started, I used a lot of like SVM, boosting, and so on. And then there's also unsupervised learning. We heard a lot here from other speakers here, and the reinforcement learning as well. And this is really, recently, it's picking up a lot. But on the knowledge side is really thinking something where I think very much problem dependent, right? And in particular, you can think of, so we are dealing with human. So there's always human anatomical model. And then there's also these images are coming from the sensors. So you can leverage some of the sensor part, like the physics and so on. And often you can get much better results. And then we are dealing with really like a 3D objects, and there's always sorts of geometry constraints and so on. And then at the different level, you can actually craft many prior constraints you can think of. So today I'm going to talk quite some of these. So that leads me to the second part of my talk, is really I'm going to show you some of the examples where how we apply this hybrid machine learning plus knowledge modeling approach to actual real solutions. The first example is this. So this is a video here. Let me play this, and hopefully you can understand easily what's going on. So we want to look at the bones here in a scan. So this is coming off one of a Siemens product. So let me play very quickly. And I think the idea is very intuitive, right? So you want to look at the rib, for example, which is 3D. It's curving in 3D space. And then to look at even one rib, you have to look at multiple slices, because they are not in the same slice, right? So the idea is really simple. Essentially, we want to find the rib center lines in a way, and then create an unfolded view of the ribs. So it's shown here. So you can augment your display, right, with this unfolded view. And then with this view, what you can get is you can look at all 24 ribs at once. And second, we also actually got the automatic labeling done as well. And then from this view, you can easily spot what's going wrong. And then you can click here and then the system will automatically navigate to the 3D location so that you can take a detailed look. So this is really a very simple thing. You just add one unfolded view, and it actually has a quite dramatic impact to the workflow. And one clinical study shows that you can actually do the reading of the ribs 2 times faster. And then further, you can actually spot more subtle fractures. These fractures could be so subtle where it's not that obvious when you look at it in 3D. However, if you don't find them, it actually might lead to big fractures, and then you are in big trouble. So you have to spot those subtle fractures. So as you will see, with this kind of display, it's easier to spot those. Actually, we can spot 10% more than routine reading. So this is really a very simple approach in a way that it combines machine learning with knowledge, right? So suppose this is the input image, and then the first thing we essentially train a classifier. At that time, we use more or less like a variant of boosting classifier. What the classifier does is to highlight the foreground, which is rib centerline. Any voxel belongs to rib centerline will be highlighted, and everything else will be the negative, should be suppressed. So after applying this classifier, you actually can get really nice rib centerline voxels highlighted. And then the second thing is we know that we are dealing with rib, which is a knowledge we know. And then we can simply do a rib cage model fitting. So it's like a deformable template. So you can deform a rib cage model, try to fit the evidence. So it's really simple. It's machine learning plus a rib cage model fitting. And after you fit, and then you can unfold it. Just simply apply certain geometric transformation. So just show you more examples, right? Let's say in this picture, now it's being difficult to see. So in this picture, there are actually some subtle fractures. I mentioned the importance of subtle fractures. So hopefully you can see once I circle this. For example, you see here, there's a little bit broken area here. And then like here, and here, these are really, small, tiny, broken pieces. And then this picture, I think from this one, you can easily spot there's a lesion here, right? And then you can click on this, and before, you need to imagine you have to look at all the slides, and of course you will see it, but it will take more time. And then this is more or less give you a holistic overview of what's going on in the rib, right? So this is osteolysis. Essentially, some of the bone materials is being loosening up. And then our algorithm is also very robust. I mentioned that. So even though we can actually dealing with incomplete rib cage as well. So in one of our patents, we said we can even actually unfold a full skeleton. So inside the human body, there are over 200 bones, and then every bone is quite unique, and it's very curved, and it could have some kind of weird shape, right? So to look at all bones, it's quite a routine, tedious work. So if we have a way, we can unfold all bones into one 2D display, and that will be very useful. Okay, so let me look at another example, which is really a very specific example, also using some of the knowledge which I called context. So let's say I present you this picture, and I tell you that there's a human eye inside this picture. So can you find this? Whoever find this, can you raise your hand? Here you go. So yeah, I think you know, if you look long enough, obviously you will see it's here. And then, but what's interesting is really, I think what's in your mind is pretty much, I'm sure, like everybody is looking at essentially row by row, column by column, until you hit the point here, you realize there's human eye, right? So this is what's going on. So that's why it takes some time, okay? And then this is the problem where I think this really like only the local context matters, because only you inspect around this area, and then you classify, well, fire up, and then you say, hey, realize, hey, is this human eye right there? But when I present you this picture and then tell you, can you see the human eye? I think everybody can see it immediately. Immediately. There's no labeling at all, right? So why? You have to ask your question, right? Why this is so easy? Why this is so difficult? So one argument, I think, is really this picture is more or less like, I call it like global context, all right? And we know very easily, like, this is human eye, this is human face, and then where eye should be located, right? So I think even we look at very locally here, if I can block the picture, if I present your, let's say, a local patch here, even from this knowledge, knowing that this is human face, you can pretty much guess where the eye is located. And there was actually this another context in a way that you look at the difference between the context between different interest points rather. So this is what I call pairwise context. So when you are basically what you are doing, looking at the different objects, and then you actually ignore things around. All right. So these are different type of contexts you can imagine. And fortunately, what we are dealing with is really like a medical image is more or less like a global context. So we can build our algorithms leveraging that, and then so that we can build a very efficient and fast algorithm at least, and potentially even more accurate, right? So I mentioned that this is really like the Vera and Jones took this idea, right, and had a sliding window approach, and then they made it really fast in the way that because they can compute features fast, right? But the algorithm itself is really depends on the number of pixels in the image. So this is not very efficient actually. And then there was I told you about this pairwise context. So how we can leverage this? One of the early approach we did is, so we actually are able to detect like 238 landmarks in 1 second from a CT volume. So this is back, again, you can think of this is back in 80 years ago, right? So it's quite amazing, I would say, engineering feat to achieve this. So the idea is really like leveraging this pairwise context. So it's rather a simple idea in the way that, you know, we did a greedy search. So we trained the multiple for each landmark, we trained the classifier, and then we first detect a first landmark, and then that landmark will tell me, based on my prior knowledge, based on my pairwise context, will predict me where the other landmarks are located. Predict a range. So what we did is we will pick this landmark with the smallest range, and then we apply this landmark classifier here, locally here. So in order to minimize the computation burden, right? And then we'll get landmark 1 and landmark 2, and once you have 2 landmarks, and this landmark itself will have also give you some predicted search range for other landmarks. So now you have 2 landmarks, and both will predict, and then we will compute the intersection of this predict region, and again pick the smallest search area and apply the landmark detection here. So as you can imagine, when you add more and more landmarks, so you actually end up less and less to search. So that's why we can really achieve a faster speed this way. So it turns out, if you write down in mathematics, this is actually a submodular maximization problem. And then this approach I just mentioned, which is a greedy search approach, it actually has some theoretical guarantee that, so we can actually find a solution where it is at least 63% of the optimal solution. So it's not that bad idea actually to do this greedy search if you can prove this is a submodular problem. And then I will tell you one last approach before I talk about deep learning, which is really simple ideas, I think, but it works really well. So the idea is really leveraging this global context. So I told you that if you have a picture with global context, and then what you can do is even if you're looking at very locally, so you can pretty much predict, let's say, the landmark, where this landmark is located, right? So this is really leveraging this global context. And then using, when I say predict, is essentially you are predicting offset vector, so which is really a regression, right? So you are given a local patch here, and then you want to regress an offset vector to the landmark of your interest. So this is really using the global context. But then another thing you can do is you can actually, once you predict, you can further verify your prediction. So which is you are using a classifier to verify locally. So this is really combining classification and the regression, and that integrates both global and the local context. And the result of that is actually, you get a fast speed because you don't have to do so many, you don't have to look at everywhere. You just look at maybe few locations to predict. So this is actually what we did. We applied the same to segment multiple organs. So what we did is we start here, and then we pick the landmarks actually on the organ boundary. And then at this patch, it will predict these landmarks will be located at these locations. And then we further call a classifier to a local classifier to verify if it's good or not. And then we move to, say, another location. We can jump a lot of pixels. We apply the same trick. It will use a regressor to predict the landmark locations, and then further verify, right? So we repeat very sparsely. And then you can summarize evidence together. So you will get a good estimate of the landmarks. And then we choose these landmarks will be on the border of the organ. And then you can imagine the next step is really like fit a shape model to these locations. And this will give you a very good boundary initialization. And afterwards, we can further refine the boundary using, at that time, is really simple method, active shape model, but we are combined with discriminative boundary models. So this is really, in a way, very simple ideas, but it is actually get us really amazing results at that point. This was published in 2013, 5 years ago. And then what we did is, what we can achieve is, in terms of accuracy, is really like the accuracy is really the inter-user variability. And we actually are able to segment, in this case, 6 organs altogether quickly. So you have 2 lungs, you have a liver, you have 2 kidneys, and a spleen. So you have 6 organs. You can segment out within 1 or 2 seconds. And this is actually nowadays part of a product, right? So with that, I hope that I convince you that when you took a machine learning approach together with your knowledge modeling, you can actually already do quite a lot, even if you don't use deep learning. Okay, now I move on to the third part of my talk, is really talking about how we can actually use deep learning within the same kind of framework. So what is deep learning, right? Deep learning is really something I think is very simple to understand. Essentially, you have an input image, and then you throw that to a deep network, which have certain parameter W, of course, and then you will get some output Y, right? So this is a very simplistic view of how you can understand deep learning, right? And then the trick, of course, is about the learning, how we can really learn this, right? And then, often you have training examples, Xi, Yi, and then you threw this to a loss, and then you formulated a minimization problem you want to minimize with respect to your parameter W, and once you learn, you apply it, right? So this is really a very simplistic view of deep learning. And then actually, in the past, we heard so much about different things, right? So number one is how can you define your network architecture? So you have different networks, which I'm not going to repeat here. You can choose. There's a huge list here. And then, of course, you can also further look at certain components inside the network. You can tweak the convolution. You can choose to use different activation function, and so on, right? And another part is what is the loss you are going to use. So this is really not that obvious, actually. So you may think like, okay, if I have a classification problem, then you often choose cross entropy. If you have regression, you have choose L1, L2. Have ranking function, then you use a scoring function, and so on. But there are also other things you have to consider, because we are dealing with special things like image. It has structures, for example, right? So you can use structure loss instead of you take each training example independently. You can combine them together, put into one loss, right? And then this is actually a very common use in image. Essentially, you pick multiple pixels, you group multiple pixels together when you compute the loss. So one of the classical example is the adversarial model, where if you put that as part of your loss, it is using all the pixels together in your loss computation. You can also form multitask loss and so on, right? And then another thing you have to consider is really look at what is your W, what is your output. So there's so many things you can consider your output. Even if you are interested in one thing, you can actually represent that in very different ways. So you have to think, what are the representations really very useful, right? So here it lists multiple typical choices people came out. But this is not necessarily the best, actually, for your problem. So for example, recognition, everybody use just labels. Then you landmark. You may use heat map, which is very common, right? And then if you have a detection, you actually use a box, and you try to regress the box location. If you have a segmentation, one choice is use mask. And then it becomes a classification problem. But there are many other options, which I'm going to show later on. And then, of course, once you pick everything you want, you have to optimize, and there are a bunch of things you have to consider. But really what I want to talk about is really how people view deep learning, right? So like this is a slide from Yang Lo-Kun, where he thinks like different people basic things deep learning very, very differently, right? So there are people who thinks like, oh, the deep learning is going to change the whole society, but for engineers like us, what we are really doing is just writing TensorFlow code and so on to put things together. And then this is actually one view coming from my advisor, Rama Charapa. He said like deep learning to him is a pasta machine. So this is really like very much, and where in Italy, pasta is really everything, not everything, is really like one of the favorite food here, right? So you prepare your ingredients and you throw that into your deep learning, the pasta will come out, all right? So it becomes really like, in a way, too simplistic. And with that, actually, I was looking at, with that point of view, right? So you may wonder which job are at risk. There was like a lot of story about like people were lost job to deep learning, right? So say they are saying like if it's a predictable, feasible work, and then you have a 38% of a chance, this job will be replaced by AI basically. And this is coming from a Wall Street Journal actually. And it is unpredictable, feasible work, and then you have 25%. So, but with this pasta machine view, I'm actually more worried. Like I think AI scientists will be the first one. The job will be replaced because once you collect all the data, you put this into the deep learning, and it's done, right? So this is really a sad part in a way that this deep network is equalizer. So no matter how many experience you have in the past, after deep learning, it means nothing. Essentially, the deep learning will take care of everything for you. And what's even worse is recently this company say auto machine learning, so everything will be done automatically. Even there's no need to tweak the network. Okay. And this is, of course, is really quite a view where I think I'm not pretty much, I would say I wouldn't really agree with this, but in a way that I see the point. But this is really my view of deep learning. It's also actually very much made public by this famous work, right? So last year at this conference of learning representation, so this is really the best paper, right? So the experiment is extremely shocking in a way that the deep learning network can fit a random label of the training data. All right? So look at this. So here you have different kind of labels, all right? So you have a true label, and of course things converge very fast. But then you put the random label, and this network will still learn, will fit. And then you can shuffle the pixels, you can randomize some of the pixels, or whatever you do. So this network is really learns. So when I say it learns, to me it's actually a super memorizer. It's really like memorizing the data you feed to the network. All right. And this, in a way, is a sad part where you have to feed the network with data. So this is really one of the view, right? So if you have a lot of data, and then if you use traditional model, this model will saturate quickly. And then you start use small network and large network, the performance becomes higher and higher, right? So it seems like one of the recipe to improve your performance is really like increase the amount of data. You just go collect the data and have them annotated, you actually get better results, which in a way is true. And then once you have more data, you may find your network is not large enough, so you just increase the model capacity of your network. So performance will go up, and then you can repeat above. So this indeed is one recipe, in a way that it is try to feed the network with more data, because the network can memorize everything. So it's likely that you can get higher performance. So this is under assumption that the testing data will falling in the same distribution of your training data. Or basically it's a coverage problem, right? With more training data, you can cover more variation, and then it's likely that when you do testing, the testing data is already within your modeling range, and hence you have good performance. So this is, of course, is one way to do this. I'm actually going to argue that you can do another trick is to, which I call is to create a knowledge gap, in a way that if you can apply a knowledge on top of your network, so my experience, at least my experience tells me that you can actually boost your performance further a little bit. And it varies, depends on the problem, or depends on the knowledge you create. So this knowledge gap, to me, is quite interesting phenomenon. I tried on many different things, and it's quite valid. So today I'm going to show you some of the examples how I can combine knowledge with a large network through deep learning to create this gap. So let's first think a little bit. Why do you think, why you think this might work, right? I think there are multiple reasons. One reason is actually when you feed more knowledge, you actually make this pattern more uniquely defined. Rather than you just present this network just a picture, you actually add more things, right? Another thing is potentially you are seeing more examples, because every knowledge you bring in, you bring some certain training examples. So the network will see more examples. And third is to sometimes when you choose different things, different representation and so on, you can actually make the problems more learnable. Not every learning problem is the same. Even though the network can, early on just mentioned, it can fit everything, but there's still things matters. Can make some difference, right? Another thing is, and very likely you can actually exploring known informations rather than you try to invent a new model, for example, right? The physics law and so on. So these are known things. If you can apply them, they are valid. So you don't have to do it by brute force learning. So let's look at how we can actually fuse the knowledge inside the deep learning framework. So this is the picture here. You have X, you have Y, you have network. So the natural way where you can apply knowledge is something like this, right? So you can put knowledge on your input side, you can put knowledge on your output side, or you can even further define your algorithms, define different networks. And then, you can apply knowledge, all right? So I'm going to start showing some of the examples how we can apply knowledge on different parts of this diagram, right? So let's say how we can apply knowledge in input. So these are typical examples, right? So one thing is if you have a multi-model inputs, let's say you have RGBD, and better you use RGBD everything rather than you just use RGB, right? Or in medical, if you have MR, you have both T1, T2, then, I think you have a better chance or higher performance if you can use both. Okay, that's one clear idea. And then sometimes even if you don't have multiple models, multiple modalities, what you can do is you can synthesize the input. All right? Or you can think of use other inputs of your problem domain. So let me show you an example, right? A synthesized input is very easy to understand. Essentially, you have an input image X, and then you put through an image-to-image network, and this network will synthesize an image at different modalities, let's say. And then you can feed both to the network, and now this network sees both input, X and X prime. And then, but it will still try to predict the same Y. So why this will be helpful? because through this part, to train this network, you have to throw more data to this. So in a way that the whole network sees more data at least. Okay? And then second, so you are having two inputs, x and x prime. And that helps you to define the pattern in a more unique way. So the network, the pattern becomes more uniquely defined. And that helps the learning as well. So this is another example where we actually use a different kind of input, which is very natural to the image, which essentially is the image coordinate. So you just put the coordinates into the input of your network. And that, it turns out, is very helpful as well. So this is, I think, is quite intuitive, in particular when you are dealing with medical images. And then after this, of course, needs a rough registration. But this is typically can be done. Once you do rough in a registration, and things are more or less in place, right? And therefore, the location information carries meaning to your model. And this is, we actually did exactly for a cross-domain image synthesis. So where we use T1 to generate T2. And this is the network, what we call the location-sensitive deep network. And then the result actually shows, indeed, it's very helpful. So if you have medical problems, I think it's time to start thinking whether I can use my location as part of the input. Okay, so that's about the knowledge in the input side. So let's look at how we can apply knowledge in the output side, all right? And this is there are multiple ways. One way is you actually can represent your stuff here in different ways. You don't have to always use a simple representation. Different representations can actually give you different results. And some will be much easier than the others to learn. Another trick people often do is you actually, in addition to your Y, you can throw another output Z, so which becomes a multitask learning. You have the same input X, you want to output both Y and the Z. And why that helps? Because the same reason, because when you add a task Z here, the Z task will bring in more training examples. So the network will see example from the Z as well. That's one reason. Another reason is there's often correlation between Y and the Z, and then there's some collaboration in between them. It also helps. Another way to apply knowledge is in fact, a priori that the output Y has to live in some manifold, in certain space, so you can apply certain price. So let me see how we can do this in the examples, right? So this is one way we proposed last year in Mikai, how we can represent a landmark. So a very typical representation of landmark is using this so-called heat map, right? So suppose this is your landmark location, and then I convolute with a Gaussian kernel, you get heat map. So this is very much spatially local representation, because you essentially ignore all the information outside this circle. The only thing you learn here is this is not close enough to my landmark. This is all negative in a way. But we know that if this is medical images, using the same reasoning, right? Suppose this is like a global context. So even faraway pixels might carry certain information for you to find the landmark. So we want to leverage that. So how we can do this is through this representation. So the idea here is something like this. Let's say you are looking at a pixel far away from this landmark. So what we want to learn is to encode, starting from here, how can we reach this landmark? So this is really directional information. If I start from here, I should, in order to quickly reach this landmark, I should first go down until I hit this diagonal line, and then I traverse over the line to the landmark. So this is a fastest path how we can go from this location to my target landmark. So in a way, this encodes a direction. So what I want to learn is, if I use this patch here, I want to learn a direction. I should go down. So this tells me where my landmark is. So if you start from here, it's the same idea. You should first go to the left, or go to your right, and then you go down. So this becomes a spatially distributed representation of a landmark, rather than very much a spatial local representation. And this representation essentially encodes my context information, even though it's far away. So this is what we did. We called it a supervised action map. Essentially, at each location, we will take action, right? Whether we go up, down, left, right, and we want to learn that. So this is the input landmark here, and this will be the targeted action map. We want to learn this action map through a network. So this is, this is input will be image, output will be also image, and each image pixel essentially carries a favorite action. And once you learn that, and then the next thing is essentially you essentially to summarize all these actions together, and then essentially everywhere it will point you towards the landmark, and you can get the final landmark location. And this is exactly what we did, and we show that in this example, which is detecting a marginal aneurysm point in apical four-chamber ultrasound views. And we see that it is give you much better result than the other representations. For example, we also tried this here. This third column is a heat map representation, right? We also tried the other, on the cardiac scans. We also tried on the OB scans, and both works much better. In both scenarios, this new representation works better. Okay, and then let's look at a very different problem. I think yesterday Daniel also mentioned we want to classify the the ultrasound views. So in this is like in a routine ultrasound abdominal scan. So where you have to acquire multiple views, right? You look at your kidney, you look at your spleen, you look at your liver, and so on. And then because these are 2D ultrasounds, we can only look at a 2D slice. So you will end up few representative views, right? In this case, we have like 10 different views. These are the really clinically used views. And then we have one label, which is none of the above views, okay? So it's a view classification problem. And then further, if you end up in certain views, right? Let's say look at the first one. This is a right kidney longitudinal view. And in this view, often you want to make a measurement. You want to measure the size of the kidney. So in that way, you end up 2 landmarks to measure a diameter of kidney in this view. And then let's say in this view, which is a right kidney transverse view, so here you actually need to measure 4 landmarks, here, 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 and then you will get 2 measurements out of this 4 landmarks. So these are really like clinical routines, right? So you took, in a clinical routine, you take ultrasound images of standard views, and then you will measure the certain size. And we want to solve this problem, basically. So the way we solve it is, so instead of treating these 2 things differently, we basically treat this as a multitask problem. So you have input image, and then one part of the network, it will classify the view. Another part of the network, it will output the landmark locations. And then we learn together, right? And this is rather simple idea, but it is quite powerful in a way that when we look at the numbers, right, look at the accuracy we can achieve in terms of, say, view classification. If we do a single task learning, we only learn this view classification, classify. And this is accuracy we can achieve. It's above 80%. And actually, just for comparison, we also asked human experts to label them. It turns out like the discrepancy between the humans are quite big for this task. It's some simple task, but it's still not that consistent. So it's about, the human consistency is about 80%. So even this single task learning is not bad actually. It's at least comparable to human accuracy. But if we do a multitask learning, so we learn both tasks together, so we're actually able to boost the accuracy quite higher. And then same thing, we find that for the measurement where we have different, remember we have different views, and each view we have to make measurements. And it's the same finding essentially. By doing this multitask learning, so we're able to get much higher much lower measurement errors compared with you basically treat each task independently. So look at here, right? So we have different measurements to make. We have like essentially almost like 20 landmarks to detect in different views. So if you detect this landmark independently, which is this row here through deep learning, it's not as good as you actually do them together through one network learning. Okay, now let's look at a different problem where we want to detect the vertebra landmarks. So we are given a CT scan and we want to find the center of each vertebra and then label them together. Okay, and this is the problem we want to address. So the idea we do is very much like this. So we first learn a deep network, try to predict each landmark using, in this case, we actually use a heat map representation. So you think of like you have, let's say you have 20 landmarks, so you output 20 different heat maps. All right. The next thing we did, in fact, is to bring back the traditional thing, the stuff, which is the shape constraint. Because we know this landmark have to form a vertebra, so there's certain shapes they have to follow. All right. You cannot do like a zigzag crazy, for example, right? And this kind of information is valid. So what we did is we actually put this global shape constraints on top of each individual heat map, and then it actually it becomes a shape-based network. It's a shape prior network, basically. And then we are able to do this in an end-to-end fashion. And then it turns out by doing so, we're able to reduce the failure quite a lot, by 14%. So this is really like, again, using, in a way, simple knowledges. So it's interestingly, we found that there are also a lot of works now essentially following this kind of paradigm, right? For example, this is from last year's CVPR paper. So where they are detecting multiple person, the poses for multiple person. And then the idea is, in addition to detecting the landmark locations for the pose, for example, each pose you have different landmark locations, right? On top of that, they further learn what they call affinity map. So essentially learning like how things aligns up between two landmark locations. So you further learn that knowledge, through a deep learning. And then in the end, they did some matching together. And they are able to get more result. So you basically use a landmark, try to learn more knowledge. And then let's look at the organ contouring as well. So this is, we did this for liver segmentation. And then one of the things we did in addition is, in addition to learning a deep learning network, where you have input CT, so you can output a mask, right? So this is, you can use, UNet, your VNet, or your favorite network. You can do that. But in addition to this, one of the things we did is actually add another adversarial trick. So you train another discriminator to tell me if this predicted mask is a fake or true. So this is very standard setting where, this is adversarial, and then, try to do minimax scan, try to further improve this, further basically tweak the learning of this segmentation network. And I think other day, Enda did a great job trying to summarize all these different things, where you could also use this as a variational autoencoder to improve your segmentation result. And we actually did a very standard way. It's just really like a GAN framework. You can try to improve your segmentation. So this discriminator, in fact, is basically an adversarial shape prior. Essentially, you see all the shape, all the shapes in your training data set, and then you use them in this fashion, right? And by doing so, we're able to reduce the error further by 34%. This is quite a dramatic improvement. Okay. And then, interestingly, we recently found a lot of things, right? We talk about segmentation. This is like from mask RCN. And then, one way to represent your segmentation mask is essentially using a multi-label mask. So this is ignoring all the information inside the mask. Everything in the mask are equal. Okay. However, there's also work where, in addition, instead of using a mask representation, what you can do is using what is called a watershed transform. So basically, you can represent a shape differently. So you try to encode information inside the shape. And then you put that into the learning, and the network actually, because the network is so powerful, it's a super memorizer, so it's going to learn this as well. So this is another different way to represent your segmentation object, right? Okay. Now, I give you one more last example how we can actually apply knowledge inside the algorithm, so that we can avoid a brute force solution. So this is the problem is about the atrial fibrillation. So if you know atrial fibrillation is essentially irregular heart beating. And you can see every year that's about $6 million spent trying to fix AFib problems. Okay? So if you have, so the main idea, the main reason why you have AFib is because this signaling is chaos inside your heart. All right. So one way to treat this is really to burn the muscles, and burn the muscles to death, and so that the signaling will not pass this area. So there's no short circuits. So everything will go back to normal. So to do burning of muscle tissue inside the heart is very obvious, a very, very dangerous thing to do, right? So one way is you have to equip with this with more images. So for example, you have the intracardiac echocardiography, which is a small, tiny transducer. You can inject into the heart. So this is like, let me show you some of the pictures, how it looks like. You can see, this guide wire, you can push the catheter, the ice catheter inside the heart. So I'm just showing you some of the pictures actually, so you can actually navigate this guide wire to different locations in order to see different parts of the heart. All right, so you can push there, you see this, and so on. But I think you got the idea, right? So what we are getting. So what we are getting is essentially a bunch of 2D ultrasound slices of 3D heart. This is very sparse because it's rather difficult to navigate these guide wires to desired locations. So these guide wires are very, very flexible, and you cannot move arbitrarily, right? So it's end up like you have multiple 2D ultrasound slices. And then what we want to do is, for these slices, we want to know where are the interesting anatomical structures, like the left atrium, the pulmonary veins, and so on. We want to find the boundary of this. And these provides a lot of meaningful information to the surgeon. So you have this, and then we want to produce the contours of different things, all right? So one way, of course, is you can treat this as a black box. So I have this input image. If I have ground truth, then I can learn a deep learning network to do the job, all right, which you can do, of course. And that turns out is not that good. It actually gives you quite a reasonable result, but we believe we can do much better. So that's why we start looking at what kind of knowledge we have for this problem. Can we use this knowledge to help us, right? So one of the knowledge that we have, turns out, is we actually know where the ice catheter is located in 3D. So in a way that if we have all these 2D ultrasound slices, we can piece them together back to 3D. So you will get something like this, because the difficulty of navigating the ice catheter, so you end up very sparse representation of a 3D heart, right? And this is actually nothing but displaying this sparse volume in a video manner. So essentially you are playing slice by slice around, let's say, this Z direction. So at each Z location, you will see different lines, right? So this is the input we have. And we saw that because everything is back into 3D, and then the learning becomes much easier, so we can actually learn directly. We can learn a 3D segmentation mask through this as input. And it turns out that this is actually quite difficult to do because the information is too sparse here. So what we did is actually we look at the other parts of the knowledge we have. In fact, we have CT scans of the heart. So what we tried to do is we actually ask the network, try to also predict a CT look output. So this is a cross-model appearance knowledge we have. And then we actually learned, seems like quite complicated manner, but it turns out we can actually do a much job by throwing this geometry knowledge, also the cross-model appearance knowledge into our models. And this is Nikai paper this year. It's accepted, and then you can see the result is better than all other different ways. Okay? So just to summarize, so talk about the trends of medical images, and the images become more. We have more modalities, and the information is more packed. So it creates a huge demand to analyze the medical images. And then I talk about, or at least justify why machine learning plus knowledge modeling is a very sensible approach to deal with this type of problem. And then we move on to deep learning, where I made an argument that I think, even if you use deep learning, you can still combine with the knowledge, so that you can create a knowledge gap in your performance. And thank you so much.